Okay, let's start. Today we will talk about processing in memory. Uh, we will talk about how to do the computation through the um, memory arrays. Particularly, I would like to use the genome sequencing as one example because genome sequencing first is very important. It's a critical application which directly can be used in precision uh, personalized health and virus um, detection. Second is a very memory intensive workloads. Each operation in the genome sequencing involve large data size, several terabytes or even zettabyte data. So all the information of a human being is recorded in the DNA. So in the cell, there are cores, and then we have the DNA, which is actually two um, piece of strands. Each strand uh, consists of different nucleotides, like AGTC. But these cells are organic, so you need some method to, detect these informations. So identify a part of the DNA is very important. For example, what's the symbol at this position in our course is very important because um, potentially this DNA can decide some features. Um, for example, we can use this DNA to improve the um, quality of some vegetables. So it's related to the food security. We can use this DNA to distinguish between human beings. So this is a important feature which can be used by the law enforcement. And of course, this DNA can be a very important factor which can decide some cancer type. So it's really important to know about this before any um, surgery happens. So knowing this, the content of the DNA is important for all these applications. Now we have the organic DNA here. We need to know um, the content of one DNA symbol in one particular position. In order to do that, we have so-called sequential machines. So you can see the smallest sequential machine uh, is at is very small. You can even hold that small machine. Um, and then this machine can generate electrical signals for this organic DNA. Different, of course, different DNA symbols will generate different amplitudes of currents. For example, A will have the largest amplitude current, while the C has the smallest current. Um, Again, uh, the cost of genome sequencing becomes smaller and smaller. The x-axis here is the age, y-axis here is the cost per megabase. Base, one base means one DNA symbol. So you can see that besides the administration fee, Of course, there are some fluctuation on the price, but the general trend is decreasing. As a result, because it's become cheaper and cheaper, now we have a lot of the genomic data, particularly with the advancing of DNA genome sequencing technologies. We have more and more advanced genome sequencing machines. So the total genomic data size on the Earth will be larger than the data size in YouTube and Twitter. You can consider the scale. So this is some information of mine. Now, by mailing some your saliva or hair is very easy for, your DNA get sequenced by some commercial companies. After the company gets the electrical signal of your DNA, the other parts, the other steps in the genome sequencing pipeline is all about the computation. So we need to proceed a lot of computation on the signals here. The first one is, of course, the translation. We need to translate the electrical signal to digital symbols like AGTC by some neural network. Nowadays, you have a BERT or transformer. So it's directly related to the attention, deep learning stuff. And then we have the alignment. Because each DNA pieces is sequenced by itself. So after the sequencing, we have a lot of small DNA pieces. How to put them together to form the large, entire, complete DNA is a problem. So we need an alignment algorithm. After the alignment, we need to do some calibration. We need to correct the errors to polish the DNA data. And then we can use another neural network to identify which position has what DNA content. After we know the content, of course, we can decide for example, the cancer type, and then we can optimize the anti-cancer therapy for some special patients. So this is a matter of life and death, and the latency of the genome sequencing pipeline is very important. But nowadays, such sequencing tests cost you maybe several days to weeks. So we have the genomic data trend, but this is our hardware trend. So clearly, we cannot use the current hardware to processing such large data. Although we can have different types of hardware platforms like many core CPU, GPU, low power FPGA, or even we can design application specific ASIC circuit to do the data processing. Eventually, the data will be blocked by memory system because you need a huge memory system to store the data. Again, we introduced the difficulty of the DRAM in the previous lecture. I don't want to repeat them here again. But the DRAM cell is not scalable. We cannot make the DRAM cell into a smaller size. So that's the reason why we need a large main memory system to store the genomic data. Second, during the genome genomic data processing, we just read a piece of data to the CPU and then do some very simple operation like the comparison. The comparison operation is actually logic XNOR operation. And then we just discard that piece of data. So there is no locality at all. We just constantly read these data from the off-chip memory and to the on-chip processing unit. Clearly, the DDR interface is the bottleneck. So these data has very small spatial locality. We basically has no reuse at all. We need to pay large power on the DDR interface. We also waste a lot of processing capability of our advanced CPU. Your CPU maybe have a lot of arithmetic units, but we just use the CPU to do some XOR logic operation. That's not a smart way to do the computation. Again, there is a very large gap between the core number and the DRAM capacity, and the core number between the core number and the bandwidth. So the bandwidth per core, capacity per core of the CPU drops every year. Some people may argue that, okay, this is not my problem. If I have enough money, I can, upload my genomic data to the cloud, so that these large companies can always have the best hardware for me to do the processing. Then, for example, if you decide to put your so-called base calling in the cloud servers, the base calling translates your electrical signal of your DNA to the digital AGTCs. Then you need to upload these signal to the server. And then the server uses a neural network to do the translation and send back you the results. Because the server will get the results first and then send it to you. So it's very easy for the untrusted server to know all your DNAs. Because your genomic data is very sensitive, so this is very dangerous. So now, not all the steps in the genome sequencing has so-called privacy-preserving awareness. Some doesn't. Some steps just ignore the privacy at all. And now, the hardware is bottlenecked by the DDR interface, which is the von Neumann bottleneck. So in the future, we hope that we can have a processing in memory unit so that we can do the computation, simple computation, stream computation without any spatial locality inside the memory RAID, so that in this way, we don't have to read the data to the on-chip cache, to the on-chip CPU or GPU. In this way, we can save a lot of data transfer energy. And then, of course, we have a fast and dense memory to store the genomic data. And then at an algorithm level, we hope that all the steps has so-called privacy-preserving awareness. So in this way, we can also utilize the untrusted servers in the cloud. So in this way, we can have different options, like we can process the data at the local, very sensitive data, of course, at the local. And then at the local, we have a very efficient hardware to do the processing. We can also upload several steps here on the untrusted servers in the cloud. So in this way, the genome sequencing latency will be significantly reduced. The cost will be significantly reduced. In this way, we can serve all the related application better, like the virus detection, virus surveillance, personalized healthcare. So we do some benchmarking. We identify some bottlenecks in different genome sequencing pipelines. So there are 3 types of genome sequencing pipeline here. So clearly the alignment is a bottleneck. So you can see this is the portion of the alignment. It heavily used FM index algorithm. Base calling, this is base calling, which is the translation your signal, electrical signal to the digital AGTC, DNA AGTC, and the variant calling. Eventually, the step which can identify the position of a DNA symbol. These 2 steps actually use the neural network heavily. So they are also bottleneck. And in this talk, we build several designs, including the hardware design and the software design, algorithm design, to attack this problem. We build fast and dense memory systems. And we also build a processing in memory accelerator for the read alignment. Eventually, we have a privacy presuming neural network. So this is the first technique. We introduced this figure in previous lecture. I don't want to repeat it again. But in this talk, I would like to use the RRAM again to do the storage, to do the main memory, and then do the processing in unit accelerator, processing in memory accelerator. So previous lecture, we introduced the phase change memory. Now we use the RRAM. RRAM is very similar to the phase change memory. The only difference here is that it uses a metal oxide to record the data. So this metal oxide layer is sandwiched by 2 metal layers. First, we can generate some filaments. Again, it's a filaments inside this metal layer. But you can see that these filaments are not connected. So if we do a set operation, we will form a complete filament, which can connecting the top layer and the bottom layer. So in this way, it shows low resistance. Or we can use a reset operation to destroy this filament. So in this way, it shows high resistance. By the high resistance and low resistance, we can represent 0 and 1. We actually can use 2 methods to achieve this. The first method is called unipolar. So we always apply the current voltage here. By different amount of voltage, we can do the reset and set. Or we can use the bipolar technique, which by applying a positive voltage and a negative voltage like this, we can do the set. And then if we apply the negative voltage here and positive voltage here, we can do the reset. Because the cross-point structure, the RRAM is very dense. It's even denser than the PCM because there's no access transistor at all. By applying a VES and a 0 here, we can set this target cell. But on the, we talk about word line and bit line. On the same word line, for the other cells, like this, we apply a 0.5 Vs on its word line. So this is a 0.5 V, and then this is a 0 voltage. So clearly you can see that there is a voltage difference, and there will be a current flowing in this way. But fortunately, we have a selector vertically stacked under the cell. So this selector can kill this current. But if we use the bipolar design, during the reset, we need to apply the voltage here and 0 here. Then we will have a voltage difference like this. Unfortunately, in this way, the selector cannot do anything about this. So this is so-called snake path current. And all the other cells on the same word line, the beta line as the targeted cell will suffer from snake path current. Although the bipolar design can achieve a smaller write current, write energy, smaller write energy, shorter write latency, even longer lifetime, and suffer from a large snake path current. So you can see the more cell you have on the same word line and bit line as this guy, the larger snake path current you will suffer. This is the reason why we cannot use the bipolar design to create a large array. So we have to limit the number of these snake path cells. By 3D stacking technique, we can even stack multiple layers together, like this. We can stack the free-flow circuit like the sense amplifier, row decoder. We studied this before in the SRAM array. So we can stack those free-flow components underneath the array, so that we can hide the cost of those free-flow circuits. But unfortunately, in order to fully cover those free-flow circuits, we need a very large array, because at least the array area will be the same as the free-flow circuit array. So in this way, the read and the write latency will be very large for the array, because the size of the array is very large. Clearly, we cannot use the bipolar RM cell to serve as the large array. We can only use a unipolar because the array size is large. But we can keep a very small bipolar array under the large unipolar array. In this way, we can use the bipolar array to serve as a cache for the large bipolar array. I'm sorry, small bipolar array will serve as a small cache as a large unipolar array. So in this way, we can access the small bipolar array first. If we have a means, we will go to the unipolar array. So this is the result. The result is very good because we increase the capacity of the off-chip memory. We also reduce the power consumption of the memory system. The second part is the processing in-memory accelerator. After the genome sequencing, we have these DNA pieces. They are so-called reads. Some of them can be directly mapped to the long reference. Then we have a hit. Others may have errors like the insert error, delete error, or substitute error. So, and then these errors introduce extra, steps. So it's very complicated to process these errors. But fortunately, most reads will have directly hit, and the heat is processed by exact match. Exact match use the FM index algorithm. You can see that for different types of DNA, exact match occupy 90% or 60%, more than 60%. I will use a very small piece of DNA to explain what's the FM index. In order to support the FM index, we need to build a Borel-Wheeler matrix. So this is the small piece of the DNA. We use a dollar symbol to indicate, okay, this is the N. This is the number 0 string. By shifting the symbols in the DNA string, we can form different strings here. So, for example, this one is a shift by 1 position. It's a left shift. So when A shift left, then A will be here. So in this way, we can generate the so-called BW matrix like this. We can sort these strings by alpha beta. So the dollar symbol is the smallest one. And then we have A, and then we have C, and then we have G, and then we have T. We can sort them in this way. So the last column here is the FME index. I'm sorry, is the BWT transformation of the array. So this is the BWT. So directly store the BWT is cost you a very large memory space. So in order to store the data more efficiently, we break the BWT into different pieces and store them separately in different bucket. Within the same bucket, we also record how many A, how many C, how many G, how many T are there in the buckets. For example, this tag indicates how many symbols are there in this bucket smaller than A. As we know, only dollar symbol is smaller than B, so this is 1. And and then how many symbols smaller than C? 2, because we have a dollar symbol and A. How many symbols are there smaller than G? We have a dollar symbol, A, and 2 C's, so we have a 4. How many symbols smaller than T? We only have 2 T's. All the other symbols are smaller than T, so it's a 5. And then this bucket, the tag in this bucket only record how many symbols in purest bucket are smaller than this symbol. For example, this bucket has no A, so only dollar symbol is smaller than A, so it's a 1. Because purest bucket has a C, then we need to plus a 1 here, so it's a 3. Purest bucket has a no G, so it's a still 4. Purest symbol have a 2 T's here, so it's a 7. So the whole structure here indicated the FM index. By looking up the FM index, we can know how many occurrences are there in the reference for one request. For example, we have this request, CGT. And then we can use this search algorithm to search this CGT. In this algorithm, we have 2 pointers. The first pointer is low, the second pointer is high. And we do the search from the end to the first symbol. This is so-called backward search. Because this is a backward search, then the first symbol we will process is T, which is the last symbol here. So we need to put the T here and count how many T's are there in an empty string. So we need to fetch the first bucket here and then count from the BWT0. BWT0 is actually an empty string. I'm sorry, the BWT0 indicated this one. BWT0 indicated the first string here, first symbol here. So the first symbol is a 1, so it's a T here. So you can see that the major operation of the FM index search is the lookup and the counting operation on the BWT buckets. So I would like to do some summarize on the algorithm. First, the so-called fetching BWT bucket indicate pointer chasing, because the current results will decide which bucket I will fetch next iteration. Because it's a pointer chasing, so the memory access are totally random. And then the major operation is the counting operation, very simple operation, which is just the counting. But the counting operation is a sequential operation because we need to count how many T in the string one by one. In order to improve the operation parallelism, we convert the counting operation into operation which calculate the Hamming distance between all symbol S string and one particular symbol. And this is so-called hardware and algorithm co-design, because we actually modified the algorithm. So I will use one example to show how can we use the ARM array to do the counting. This is a very normal ARM array. And then the white cell indicate an empty ARM array, which has no filaments at all. So if there's no filaments in the ARM array, we cannot do the set or reset because it shows high resistance. This one shows the high resistance. We have a broken filaments in this cell, and this one shows the low resistance set ARM cell. So we encode the AGTC by 2 bits like this. 0 indicate low voltage and 1 indicate high voltage. And then we, in order to count how many T are there in AT, we convert this problem to the Hamming distance calculation between TT and AT. So for example, the Hamming distance between these two guys is 1. And the length of the string is 2. So if we use 2 minus 1, there is only 1 T in this string. And then we can directly apply the voltage representing these arrays on the ARM array. And then the cell will flip based on the voltage on its two ends. For example, here we have a 0, but here we have a 1. Here we have a 0, here we have a 1. So it will be set. This one will be also set, but these two will not change because they have the same voltage on two ends. So in this example, 2 cells are set. When we apply the read voltage on the arrays, then we can sense only only 2 cells are actually changed. We have some transistor which can limit the current. So in this way, we can know that only 1 cell is changed. We know this one is actually, the one here. By other simple operation, we can know, okay, the Hamming distance here is 1. In this way, we can do the counting operation inside the RM array. That's a very, fast operation, very good operation, because we don't have to read the data back to the on-chip CPU. We can save a lot of power on the DDR interface. The last part is to design a, neural network algorithm which can preserve your privacy. So if you naively upload your private sensitive data to the untrusted server on the cloud, it's very dangerous. So Pierre's work proposes a so-called homomorphic encryption operations. The so-called homomorphic encryption operations can enable you to do the computation on encrypted data. So the user will encrypt their data into some ciphertext, and then they only upload their ciphertext on the server. The server do a lot of operation on the ciphertext and then return a encrypted results. Only the user have the secret key, which can decrypt the results and know whether I have a cancer or not. So in this way, the server doesn't even know what input it has and what the result it has. Only the user can know the content of a user. The input and output. All the homomorphic encryption operations are based some principle like learning with errors. And there are 2 types of homomorphic operation. One is the addition. The other one is a multiplication. I will use the addition as one example to explain the homomorphic encryption. So the encrypted A plus encrypted B equals to the encrypted A and B. So this is the meaning of a homomorphic encryption. Assume the encryption method is 2 multiply X. And of course, this is not a safe encryption scheme. I just want to give you one simple example. Assume multiply 2 is your encryption scheme. Then the number divided by 2 is your decryption scheme. The plain text is 10 plus 5. After I do the encryption, we have a 20 and a 10. And then we can do the addition on them. The result is 30. And then I do the decryption, which is use this number divided by 2. And then I get 15. So this is the same as the result of a plain text addition. So this is the neural network. The neural network is a network which has a lot of neuron. Each neuron has a lot of weights and a lot of inputs. And we will use the input multiply the weights and accumulate them together. You can see that this is addition. This is addition. This is multiplication. All of them are homomorphic. So it's very natural to use homomorphic to do the computation. But unfortunately, we still have activation on the neural network, which is ReLU, which is a nonlinear operation. Unfortunately, the normal homomorphic operation cannot support non-linearity here. Pierre's work proposed to use the square function, this curve, to approximate this ReLU curve here. And of course, you can see they are totally different, so it's not accurate. In this way, you sacrifice a lot of accuracy. In order to win this accuracy back, it's possible for you to use a high degree polynomial to mimic the activation. But when you increase the degree, the computation overhead also increased. As a result, the activation will consume maybe 99% of your execution time. Then we proposed to use a novel new HE scheme to support the activation. This is so-called TFHE, which can support the homomorphic logical operation. For example, you can do a homomorphic AND, homomorphic OR here. Clearly, by this logic gates, we can build a ReLU, homomorphic ReLU here. So if the homomorphic encryption TFHE is so good, why Pure's work didn't use it? This is because the TFHE can only support a bit level logical operation. If we use a TFHE to support this multiplication, you can see that one multiplication will be broken into, at least 16 multiplication here. In this way, the time of multiplication will be significantly increased. So if we naively use TFHE to build the neural network, this is the overhead we introduced. We didn't reduce the latency, but we increased the latency a lot, doubled almost. But the good news is that we can have an accurate neural network. The accuracy increased. So in order to reduce the latency, we propose to use the log2 quantization to convert the multiplication to the shift and add operation. By the log2 quantization, we can convert this multiplication and addition to the shift and add. For example, if you originally you have a 10 multiply 0.6, then we can, quantize the 0.6 to 0.2, which is a 2 minus 1. 2 minus 1 is a right shift 1 bit. The TFHE can efficiently support this homomorphic shift operation. So in this way, we can reduce the TFHE based neural network latency a lot without sacrificing the accuracy. So we also designed some accelerator to accelerate the homomorphic operations. And the homomorphic operation itself also very memory consuming. So now basically we use different algorithm, different hardware design to support the genome sequencing applications. Any question? If no question, please go to this OCQ website. I really appreciate all your feedbacks. If you have any question about this OCQ, about the content I present today, please email me. Thank you very much.
Thank you.